So we've talked about regressions where you're trying to predict some value given some feature that you're measuring. Basically, you're creating a line that predicts things given some measured feature. But what if you have more than one feature? What if there's more than one thing that influences the thing that you're trying to predict? Well, that's where a multivariate regression comes in. Multivariate means many variables. So if you have more than one feature that might contribute to something, like, for example, the make and model of a car and its mileage and the number of doors and size of its engine, those all might have an influence on the price of that car in a fair market. That's the case where a multivariate regression might come in handy. So let's see what's involved. Let's dive into multivariate regression, just a regression that takes more than one variable into account, more than one feature. Concept's actually pretty simple. It's just answering the question, what if I have more than one variable influencing the thing that I'm trying to predict? So basically I'm doing a regression that I don't just have one feature that I'm measuring to try to predict some value, I have many features that might come together. So an example, that might be predicting the price for a car based on its many attributes. The car has a lot of different things you can measure that might influence its price, such as its mileage, its age, how many cylinders it has, how many doors it has, things like that. You can actually take all of those into account potentially and roll that into one big model that has many variables as part of it. And the way we do this is actually pretty simple. So we just have, instead of a coefficient attached to some single variable, we have multiple terms here with multiple variables. So we can say that we can predict the value price based on some constant value alpha times some coefficient beta 1 times your first feature, say it's mileage, plus some coefficient beta 2, which might be multiplying some other feature like age of the car, plus beta 3 times the number of doors, whatever you want to do. And those coefficients are just measuring how important each factor is to each actual end result. Now, assuming, of course, that all of your features are normalized, otherwise that coefficient will also be working in how to scale that feature into the final result as well. So that can be informative. If you actually work out the values of beta 1, beta 2, beta 3, whatever you have, that can tell you a little bit about what features are actually important. So if you end up with a very low coefficient for a given feature after things are normalized, that might be nature's way of telling you that that feature isn't actually very important for predicting the thing that you're trying to predict. And that can help you simplify your model by eliminating data that you don't need. So that's a cool thing. Now, this all still uses least squares. So in our notebook, we're going to use something called OLS. That stands for ordinary least squares, and it can handle multiple features like this. So we can still measure the fit of this thing overall using r squared. Nothing's different there. And another thing that we need to point out is that this whole thing assumes that there's no dependency between these different features. So notice that I'm treating all these features independently with their own coefficient. So if there is in fact a relationship between these features, this model will not capture that. And this is actually an example of where that would be the case. So for example, the mileage on a car I think would be very highly correlated to the age of the car. And this model will not capture that. In fact, you'll probably be just fine just using mileage or age independent of each other. But this can at least tell you which one is more important. So with that, let's dive in and actually fire up a notebook and see how it works. There's something called the stats models package that makes things easy and offers the OLS model that we can use to just go off and make it chug away and do it all for us. So let's play with multivariate regression. The stats models package makes it pretty easy. So let's dive into an example here and play around. Open up the multivariate regression.ipynb file if you haven't already, and you can follow along. So we talked about trying to do predictions of car prices based on the many attributes of a car. Let's make that real. Go ahead and kick off this first block here, and that will suck down a Excel spreadsheet that I created offline that just has fabricated data about various cars and the amount that they sold for, and some data about those cars, and it will load that into a pandas data frame. So if you have internet connectivity, that should come right down. And if you go on further here, we can take a little peek at that, and you can see that we have a price column that represents the price that each vehicle sold for, the mileage of that vehicle, the make, model, trims, and type, body type, number of cylinders, liters of the engine, number of doors, and some binary data, whether it has cruise, control, sound system, or leather. So we can have some fun with this. So our strategy is going to be to try to predict the price based on, let's pick 3 of these features to try that we think intuitively might make sense. Now, a little note here about categorical data. A lot of this data is categorical, make, model, and trim, and type. There's no real order to that. They're just strings that represent some brand name, right? So with categorical data, you can't really use that for a regression model. Remember, at the end of the day, we're just creating coefficients in front of numerical values that represent each feature. And if there's no real way for me to map Buick to a number, That's not really something that's useful for a regression, not just multivariate regression, but any regression in general. So I'm going to skip those over. Now, if they were in fact ordinal values where there was some inherent order to those strings that I could then convert them to numbers, that would be fair game. But there's not really a straightforward way of doing that with something like Buick. Maybe you could sort it by MSRP or something, but let's not go there, okay? Instead, I'm going to pluck out mileage, cylinders, and doors as the features that I'm going to play with. They're my candidates for things that I think might make a difference on the price. So if you scroll down here, all I'm doing is creating an X data frame that plucks out the mileage, cylinder, and doors features. Okay, so this is my feature data, and it has 3 dimensions to it. And the value I'm trying to predict, I'm putting in the Y data frame, and that's going to be my price column. Now I'm also going to scale all of the mileage, cylinder, and doors data to be normalized into the -1 to 1 range, and that's what the scale.fit transform call here does. So that's just saying take all the mileage, cylinder, and doors and scale them down into -1 to 1. That way I can look at the coefficients that I end up with on each term, and I can compare those coefficients in a meaningful way. I will print out what that looks like, and then I'm going to actually create an OLS, ordinary least squares model, using the stats models package that we installed way back at the beginning of the course, and call fit to actually create that model based on the features and X and the value in Y, the price that I'm trying to predict. I will then print out a summary of that model so I can see what it looks like internally. So let's go ahead and kick that off. That's the interesting part. So here you have it. You can see that the mileage, cylinder, and doors data has all been normalized from -1 to 1, so I can make them comparable. We can ignore these warnings here about converting floats to integers, not a big deal. Down here is where things get interesting. So we can see that for the mileage, cylinders, and doors, these are the coefficients I ended up with toward their individual contributions toward the final price in my model. And it turns out that if you look at the absolute values of these, cylinder actually turned out to be the most important term there. So that ended up with the highest absolute value coefficient, which is a little bit of a surprising result. You would think that the number of doors or the mileage would actually have more of an influence, but it turns out that the number of cylinders is actually a more prominent feature of this model. And, you know, if you stop to think about it, you can rationalize that. I mean, if you have an 8-cylinder muscle car, that's probably going to cost more than a 4-cylinder, economy car, right? So it kind of makes sense when you think about it. And you kind of have to ask yourself the question, could I have figured that out sooner? Well, yeah, I mean, sometimes you just have to take a look at your data at a higher level and do some higher analysis on it to try to figure out whether or not things actually matter. So for example, I could have figured out pretty easily if the number of doors actually made a difference on the price without doing all this fancy multivariate regression stuff. I could have just broken up the number of doors and printed out the mean price for each category of number of doors. So if I do that, you can see that there's not a big difference in price between the number of doors here. The average 2-door car sold for $23,000 and the average 4-door sold for $20,000. So that's not a great predictor. A little bit of a surprising result, but again, the 2-door cars are probably sports cars, which probably sell for more money, right? So, plus there's a small data set, so there's not a whole lot of information there. So I could have learned much more easily that doors didn't really matter. And up here I can see, just from the coefficients I ended up with that, yeah, doors don't matter compared to the number of cylinders. That's actually a more important statistics for predicting the price of the actual vehicle. So if you want to get your hands dirty, go ahead and do so. Some ideas here. Mess around with that fake input data. See if you can actually create a meaningful relationship between the number of doors and the price. So just go ahead and hack up that Excel spreadsheet and load it from your hard drive instead of from the internet here and have some fun with it. Why stop at 4 doors? Maybe you live in some alternate universe where there are 8-door cars out there. I don't know. Go wild. And another thing you might want to mess around with is actually dealing with that categorical data. Is some of it really ordinal in nature? Is there a way I can actually organize the different makes and models in terms of their average MSRP when the cars are new? That might be a reasonable thing to do. So sometimes you do have to deal with categorical data. So see if you can actually work that into your model in such a way where you're converting those categories into integer values that actually have some inherent order to them, some meaningful order. And you might be able to get some interesting information that way as well. So go have some fun with it. So there you have it, multivariate regression. It's not really that complicated. It's really the same concepts as single variable regression. It's just you have multiple terms, one for each feature that you're measuring to make a prediction. So not that hard, really. Just remember that dealing with categorical data can trip you up sometimes. Anytime you're doing a regression, whether it's multivariate or not, categorical data isn't going to throw you awry unless you can arrange those categories in some sort of numerical order that makes sense. But given that you have numeric feature data, you can use the techniques of least squares to actually do multivariate regression pretty easily using NumPy and SciPy.